Okay.
Thanks to the attentiveness of Peter over there, I have to make a small but important correction to the example of PDTs that is still on the whiteboard, because it turns out that the reduced PDD that I drew was wrong. Actually, if you look at these two Q nodes in the unreduced PDD, you realize that they can be collapsed, because actually they have the same true and false branches. And that means that here the top P node has the same child for its true and false branch, which according to the rules of reduction means that you can remove this P node altogether. But the actual reduced PDD is not the one that I showed before the break. It's actually the one that doesn't even have a P node on top. Which is a bit surprising. It was surprising to me, but I tried to figure it out. And actually, I now believe that this is correct. So I've had on the slide wrong for about 5 years, nobody noticed. But if you think of this formula, then I do believe that P XOR Q XOR P XOR R is actually logically equivalent to Q XOR R, which is this PDD over here. So it's easy to make mistakes. I just demonstrated that it's easy to make mistakes, but I now believe that this is the correct version. Okay, and I will correct it on the slide, but probably not very soon because I'm going on holiday tonight. Okay, let's go a step further. You've had enough of propositional logic. Let's have a bit of fun with skating. This is an excerpt from a newspaper. It's the ICUS in the NRC, where people submit an email or a small story of no more than 150 words, I believe, and this gets printed on the back page of the best newspaper in the Netherlands every day. Oh, sorry, that was a judgmental statement. One of the quality newspapers in the Netherlands. And this is about skating. So, and why do I show you this? Well, this is, of course, it's an ordinary story, but this lends itself to translation into logic quite well. And it's a funny story to do. So, where shall I start? The I in this story meets two girls on the skating rink and helps them with their bootlaces, and then the first girl asks the I person, "Are you a girl or a mother?" Well, this in itself is already quite an interesting statement. Are you a girl or a mother? If you translate this into logic, what would that look like? I mean, there is a hidden assumption in this question, actually.
If you are both a girl and mother, it can be true?
Yes, exactly. I mean, apparently, there's the hidden assumption that either you are a girl or a mother. Right? There's actually an exclusive or, I would almost say, between being a girl and being a mother. So implicitly, this first questioning girl is saying, for all persons, either this person is a girl or this person is a mother. And it cannot be the case that they are both, and it cannot be the case that they are neither. So then she goes on, because the second girl then says she's a mother because she can skate but not make curves, just like my mother. So this second girl is actually making an inference, and she's just essentially saying there's an implication there between being able to skate but not being able to make curves and being a mother, which again is a very funny kind of observation, right? But now we're talking about two more properties of persons, namely the ability to skate and the ability to make curves. So now we have four properties of persons: being a girl, being a mother, the ability to being able to skate, and being able to make curves. And essentially all that these girls are saying can be translated into logical statements involving those four properties of persons. We can translate this one by saying, for all persons, if they can skate but not make curves, then they must be a mother. And then the first girl goes on and, well, makes some pretty acute observations about the invalidity of the second girl's observations. So I think that the first girl definitely would be a candidate for a study like computer science, and certainly for a course like logic, but the story doesn't say whether that is the outcome. Actually, this is from 5 years ago, and by now maybe these girls have entered secondary school, and in 5 more years they will sit here in benches. Anyway, so this is meant to illustrate that we are now talking about statements that actually involve individuals. And we're making inferences about all individuals, or there cannot be an individual. And that is very much more powerful and much more interesting than what we could do using propositional logic. So propositions will capture only global facts, do not reason about individuals. We'll now introduce this notion of predicate logic formally, which does allow you to do these things, and we do it stepwise, using the same steps that we've done using for propositional logic. So first I'll talk about the syntax, then I'll talk about semantics, then I'll talk about some proof methods. And the proof methods are essentially extensions of the things we've seen, so this allows me to go a little bit quicker, but of course things get more interesting at every point. So what about the syntax of predicate logic? Well, first of all, what about the syntax of predicates? The notion of a predicate, what is that? Predicate is actually essentially a property of individuals or a relation between individuals. And that means that we can talk about concrete individuals, which are denoted by constants, or we can talk about variables. So there are two ways to talk about individuals. There are constants and there are variables. The constants have a fixed value, that's why they're called constants, whereas the variables still must be assigned a value. I mean, actually the word variable, in the way that you're probably most used to it from programming, is a bit misleading here. Because a variable, certainly in imperative programming, is a location that can change its value. And everybody thinks that this is why they are called variables, because their value can vary. Yeah? That's a natural thought. Historically, that's not the right explanation. Historically, this word variable, as used in programming languages, actually came from mathematics, where the variation is not that at some point the variable has some value and later on the same variable may have a different value. Instead, the variation in mathematics is just you don't know the value. It could be one thing, it could be another thing, but mostly in the setting of mathematics, once it's got assigned the value, that value doesn't change anymore. And that is what we'll do here. So maybe it's good to realize this difference. When I talk about a variable, it's something that doesn't have a fixed value, but once I assign it a value, then that value is fixed. It doesn't change in the lifetime of the variable. Yeah, so please keep that in mind. Okay, then on top of such terms, I will build atoms. And atoms are either propositions, as we already knew them, or they are predicates applied to a list of atoms. And a list of atoms is nothing but a comma-separated list of constants and variables. So those will be the atoms of my formulas. On top of those atoms, I can build the formulas in the following ways. An atom itself is already a formula, just like a proposition was already a formula. Or I can apply an operator, like the operators we've seen before, binary or negation. Or, and this is new, I can quantify over variables. And these, I'm sure you've met these notations. For all x something holds, there exists an x such that something holds. These are called quantifiers, and this must be a variable, like the variable variable that I introduced before. This essentially is the syntax of predicate logic. So what is new with respect to propositional logic is the fact that we have atoms that are parameterized by a list of either constants or variables. Secondly, that we have these constructs to quantify over the variables. Yeah, I think that all of you have seen this before in some form or another. Is that true, or is there somebody to whom this is completely new? Good. Your silence is consent, so you have seen it before. Okay, some abstract examples just to loosen your mind up a bit. I'm just using meaningless names here, but I'm asking you to imagine a scenario where this formula, for instance, has a meaning. So let's look at the first formula. For all x, for all y, p x comma y implies p y comma x. Can you give me a setting in which this makes sense?
Equality.
Equality. If p is it has two parameters, meaning it's a binary relation. So this expresses the property of some binary relation p. Yeah, and the property that it expresses is that if p holds for x comma y, that also holds for y comma x, which is true, for instance, for equality.
Is the order of x and I important here?
It's very important. Yes. So when I say an atom is a name together with a list of arguments, the order of that list of arguments is extremely